Welcome to Fun Facts Online, the show that unpacks the incredible science behind our everyday world. I am your host, and today we're tackling a question that feels both simple and impossibly complex. How does your phone know, with pinpoint accuracy, exactly where you are on this planet? When you tap on a map, and a little blue dot appears right on top of you, it feels like magic. But it's not magic. It's an incredible symphony of physics, engineering, and mathematics, a system that has quietly become one of the most important technologies of the modern age. We're talking about the Global Positioning System, or GPS, and the whole family of navigation satellites orbiting high above our heads. This invisible web doesn't just help you find the nearest pizza place. It underpins our financial markets, our emergency services, and even how we grow our food. So today, we're going on a journey from the dawn of the space race to the mind-bending theories of Albert Einstein to uncover the secrets behind this ubiquitous navigator. Get ready, because the science of how we find our way is more amazing than you could ever imagine. The story begins, as many great technological tales do, with the Cold War. In 1957, the world was stunned when the Soviet Union launched Sputnik 1, the first artificial satellite. As it beeped its way across the sky, a couple of scientists at the Johns Hopkins Applied Physics Laboratory made a groundbreaking observation. They noticed they could track Sputnik's exact orbit by analyzing the Doppler effect on its radio signal. You know the Doppler effect. It's why an ambulance siren sounds higher pitched as it comes towards you, and lower as it moves away. The scientists realized that the frequency shift in Sputnik's signal told them how it was moving relative to them. And then, they had a revolutionary idea. If you can figure out a satellite's position from the ground by listening to its signal, then the reverse must also be true. A receiver on the ground could figure out its own location by listening to signals from satellites with known positions. Boom! The core concept of satellite navigation was born. This led to the first system, called Transit, used by the US Navy in the 1960s to track their submarines. But the military wanted something better, faster, and more robust. So in 1973, the US Department of Defense launched the GPS project. The first satellite went up in 1978, and the full system of 24 satellites was declared operational in 1993. For years, the best, most accurate signal was reserved for the military, while civilians got a fuzzier, less precise version. But in the year 2000, that all changed. The policy, known as selective availability, was switched off, and suddenly, hyper-accurate GPS was available to everyone on Earth for free. This single act unleashed a tidal wave of innovation that has completely reshaped our world. So how does this system, with its origins in tracking Soviet satellites, actually work? At its heart, GPS is a system of three parts working in perfect harmony. First, you have the space segment. This is a constellation of more than 30 satellites, orbiting about 20,200 kilometers, or 12,550 miles, above the Earth. They're arranged in 6 different orbital paths, which ensures that from almost any point on the planet, you can see at least 4 satellites at any given time. Each satellite is basically a very, very fancy clock in the sky, constantly broadcasting a message with its exact location and the current time. Second, there's the control segment. This is a network of ground stations around the globe. Their job is to constantly track the satellites, monitor their health, and upload tiny corrections to make sure their position and time data is absolutely perfect. They're the diligent mission controllers, keeping the whole fleet in tune. And finally, there's the user segment. That's you. Or more specifically, the billions of GPS receivers in our phones, cars, watches, and airplanes. These little devices are the listeners, detecting and decoding the signals from space to figure out their location. The fundamental principle behind it all is a concept called trilateration. Imagine you're lost in a field, but you know you are exactly 5 kilometers from town A. 7 kilometers from town B, and 6 kilometers from town C. What do? You could draw a circle 5 kilometers wide around town A, a 7-kilometer circle around town B, and a 6-kilometer circle around town C, the single point where all 3 circles intersect. That's your location. GPS works the same way, but in 3 dimensions with spheres instead of circles. A GPS receiver in your phone measures its distance from a satellite. It does this by calculating how long it took for the satellite's radio signal, traveling at the speed of light, to reach it. Distance equals speed times time. With the distance from one satellite, your phone knows it's somewhere on the surface of a giant, imaginary sphere with that satellite at its center. A signal from a second satellite creates a second sphere. The intersection of those 2 spheres isn't a point, but a perfect circle. So you bring in a third satellite. The third sphere intersects that circle at 2 possible points. Usually, one of those points is a ridiculous answer, like thousands of miles up in space or deep inside the Earth, so your phone can easily figure out which one is you. But there's a catch, and it's a big one. This whole method relies on absolutely perfect timing. The clocks on the satellites and the clock in your phone have to be perfectly synchronized. Even a tiny error, a millionth of a second, would throw your position off by hundreds of meters. And while the satellites have hyper-accurate atomic clocks, your phone definitely does not. That would be wildly expensive and bulky. This is where the 4th satellite comes in. By getting a signal from a 4th satellite, your receiver can solve for a 4th unknown variable, its own clock error. It essentially says, okay, I know my distances to satellites A, B, and C seem a bit off. Let me use the signal from satellite D to figure out exactly how fast or slow my own internal clock is running and correct for it. With that correction, it can then nail down its latitude, longitude, and altitude with incredible accuracy. So, 4 satellites are the magic number for a precise 3D fix in time. Now, let's dive into the really mind-bending science that makes this all possible. Because to achieve this level of precision, we need to rely on 2 of the most profound concepts in physics: atomic clocks and Einstein's theory of relativity. First, the atomic clocks. Each GPS satellite carries multiple atomic clocks, which are the most precise timekeeping devices ever created by humanity. Unlike a quartz watch that relies on a vibrating crystal, these clocks use the incredibly stable and predictable vibrations of atoms, like cesium or rubidium. The frequency of these vibrations is so constant that a modern atomic clock might only lose or gain a single second over millions of years. This isn't just for show. This precision is absolutely critical. A timing error of just 1 nanosecond, that's a billionth of a second, translates into a position error of about 30 centimeters or 1 foot. The atomic clocks are the unwavering heartbeat of the entire GPS system. But even with perfect clocks, there's another hurdle, and it comes from Albert Einstein. His theory of relativity, which describes how gravity and motion affect time and space, isn't just some abstract concept for physicists. Without accounting for relativity, GPS would be hopelessly inaccurate, failing within minutes. There are 2 parts of relativity at play here. First is special relativity, which says that for a moving object, time slows down. The GPS satellites are hurtling through space at about 14,000 kilometers per hour. Because of this immense speed, their atomic clocks actually tick slightly slower than clocks on Earth. But then there's general relativity, which says that gravity also affects time. The weaker the gravity, the faster time passes. The satellites are way up in orbit, where Earth's gravitational pull is much weaker than it is down here on the surface. This means the clocks on the satellites tick slightly faster than clocks on the ground. So you have 2 relativistic effects working against each other. One slows the clocks down, the other speeds them up. When you do the math, the effect of weaker gravity is stronger. The net result is that the clocks on GPS satellites run faster than clocks on Earth by about 38 microseconds every single day. That might not sound like much, but if we didn't correct for it, the system would accumulate a positioning error of about 10 kilometers every single day. Your phone would tell you you're in the next town over. The engineers designed the system to account for this. The clocks on the satellites are actually set to tick at a slightly different rate to counteract relativity, ensuring the time signal they broadcast is accurate from our perspective here on the ground. So next time you use Google Maps, you can thank Albert Einstein, because his mind-bending theories are what's keeping that little blue dot right where it should be. For a long time, GPS was the only game in town, but today it's part of a much bigger family. The proper term is GNSS, or Global Navigation Satellite Systems. Several other countries have built their own constellations, creating a truly global network. Russia has its system called GLONASS, which was developed around the same time as GPS. The European Union has Galileo, a system specifically designed to be under civilian control, offering incredibly high accuracy. And China has its Beidou system, which became fully global in 2020 and has a unique design that provides extra coverage over the Asia-Pacific region. There are also regional systems, like India's NAVIC and Japan's QZSS, designed to enhance service over their specific territories. So why is this global family of systems so important? Because modern receivers, like the one in your smartphone, are multi-constellation receivers. They don't just listen for GPS satellites, they listen for signals from GLONASS, Galileo, and Beidou all at the same time. This has huge advantages. With more satellites in the sky to choose from, your phone can get a location fix much faster and more reliably. This is especially true in challenging places like urban canyons, the streets between tall buildings, or in dense forests where your view of the sky is blocked. Having more satellites means you're more likely to see the 4 you need. It also improves accuracy and makes the system more robust, because your phone can cross-check the signals from different systems to get a more trustworthy result. Meter-level accuracy is amazing for most of us, but what about applications like self-driving cars, precision agriculture, or land surveying? For those, you need to get even better. You need centimeter-level precision. This is where augmentation systems come in. These are systems that enhance and correct GNSS signals to make them even more accurate. One of the most powerful techniques is called real-time kinematic, or RTK. RTK uses 2 receivers. One is a stationary base station at a precisely known location. The other is the rover, like a self-driving tractor or a surveyor's pole. The base station knows its exact position, so it can calculate the tiny errors in the satellite signals it's receiving in real time. It then broadcasts these error corrections to the rover. By applying these corrections, the rover can determine its position down to a single centimeter. This technology is revolutionizing industries. In precision agriculture, tractors guided by RTK can plant seeds and apply fertilizer with incredible accuracy, reducing waste, saving money, and protecting the environment. In disaster management, GNSS is used to map damage after an earthquake and guide rescue teams. And scientists use it to monitor the movement of tectonic plates and the melting of glaciers, giving us vital data on our changing planet. So what does the future hold? The world of global navigation is constantly evolving. The trend towards a multi-GNSS world will continue, with more satellites and new, more robust signals, making the entire system even more reliable. But the real game changer is the integration with other technologies. Artificial intelligence and machine learning are being used to intelligently filter out signal errors and fuse data from multiple sensors, like GNSS, cameras, and motion sensors, to provide a reliable position even when satellite signals are weak or unavailable. This is crucial for autonomous vehicles. And when you combine GNSS with 5G networks and the Internet of Things, you open up a whole new world of possibilities, from tracking shipping containers across the globe to monitoring environmental conditions with billions of tiny sensors. The ultimate goal is what experts call PNT everywhere: precise positioning, navigation, and timing, available to everyone, everywhere at all times. That includes the tough spots, like indoors, underground, and even underwater. From its secret origins in the Cold War space race, the science of global navigation has become a global utility we all depend on. It's a stunning testament to human ingenuity, a delicate dance of satellites orbiting thousands of kilometers above us, kept in check by atomic clocks and Einstein's theory of relativity. So the next time you pull out your phone to navigate to a new restaurant or track your morning run, take a second to think about that silent, invisible symphony playing out in the space above, an incredible network that guides us with ever-increasing precision on all our journeys, both great and small. Thanks for listening to Fun Facts Online. Join us next time for another deep dive into the science that shapes our world.